Good evening, and welcome to Boring Books for Bedtime. I hope tonight's installment provides all the boredom your busy brain needs to quiet down and let you get some sleep for once. So lie back, adjust your volume, take a nice deep breath, and off we go. Tonight we'll be relaxing to one of the great works of science. It's The Principles of Chemistry by Dmitry Mendeleev, translated from the Russian by George Kamensky, ARSM, of the Imperial Mint, St. Petersburg, member of the Russian Physico-Chemical Society. Edited by T.A. Lawson, BSc, PhD, Examiner in Coal Tar Products to the City and Guilds of London, Institute Fellow of the Institute of Chemistry. Published by Longmans, Green & Co., 39 Paternoster Row, London, New York, and Bombay, 1897. In 2 volumes. Volume 1. Preface to the English translation. The first English edition of this work was published in 1891, and that a second edition is now called for is, we think, a sufficient proof that the enthusiasm of the author for his science and the philosophical method of his teaching have been duly appreciated by English chemists. In the scientific work to which Professor Mendeleev's life has been devoted, his continual endeavor has been to bring the scattered facts of chemistry within the domain of law, and accordingly in his teaching he endeavors to impress upon the student the principles of the science, the generalizations, so far as they have been discovered, under which the facts naturally group themselves. Of those generalizations, the periodic law is perhaps the most important that has been put forward since the establishment of the atomic theory. It is therefore interesting to note that Professor Mendeleev was led to its discovery in preparing the first Russian edition of this book. It is natural, too, that the further application and development of that generalization should be the principal feature of this, the latest edition. There are special difficulties in rendering the Russian language into good English, and we are conscious that these have not been entirely overcome. Doubtless also there are errors of statement which have escaped correction, but we believe that the present edition will be found better in both respects than its predecessor. We have thought it our duty as translators to give as far as possible a faithful reproduction of Professor Mendeleev's work, the 6th Russian edition, without amplifying or modifying his statements, and in this we have the author's approval. Although other duties had prevented Mr. Greenaway from undertaking the care of the present edition, he has been kind enough to give us the benefit of his suggestions on several points. We also wish to thank the managers of the Royal Institution for permission to reprint the lecture delivered at the Royal Institution by Professor Mendeleev in Appendix 1, and to the Council of the Chemical Society for permission to reprint the Faraday lecture which forms Appendix 2. In conclusion, we are indebted to Mr. F. Evershed, who has given us much valuable assistance in revising the sheets for the press. George Kamensky and T.A. Lawson. August 1897. Author's Preface to the 6th Russian edition. This work was written during the years 1868 to 1870. Its object being to acquaint the student not only with the methods of observation, the experimental facts, and the laws of chemistry, but also with the insight given by this science into the unchangeable substratum underlying the varying forms of matter. If statements of fact themselves depend upon the person who observes them, how much more distinct is the reflection of the personality of him who gives an account of methods and of philosophical speculations which form the essence of science. For this reason, there will inevitably be much that is subjective in every objective exposition of science, and as an individual production is only significant in virtue of that which has preceded and that which is contemporary with it, it resembles a mirror which in reflecting exaggerates the size and clearness of neighboring objects, and causes a person near it to see reflected most plainly those objects which are on the side to which it is directed. Although I have endeavored to make my book a true mirror directed towards the whole domain of chemical changes, yet involuntarily those influences near to me have been the most clearly reflected, the most brightly illuminated, and have tinted the entire work with their coloring. In this way, the chief peculiarity of the book has been determined. Experimental and practical data occupy their place, but the philosophical principles of our science form the chief theme of the work. In former times, sciences, like bridges, could only be built up by supporting them on a few broad buttresses and long girders. In addition to the exposition of the principles of chemistry, it has been my desire to show how science has now been built up like a suspension bridge, supported by the united strength of a number of slender but firmly fixed chains, which individually are of little strength, and has thus been carried over difficulties which before appeared insuperable. In comparing the science of the past, the present, and the future, in placing the particulars of its restricted experiments side by side with its aspirations after unbounded and infinite truth, and in restraining myself from yielding to a bias towards the most attractive path, I have endeavored to incite in the reader a spirit of inquiry which, dissatisfied with speculative reasonings alone, should subject every idea to experiment, encourage the habit of stubborn work, and excite a search for fresh chains of evidence to complete the bridge over the bottomless unknown. History proves that it is possible by this means to avoid two equally pernicious extremes: the utopian, a visionary contemplation which proceeds from a current of thought only, and the stagnant realism which is content with bare facts. Sciences like chemistry, which deal with ideas as well as with material substances, and create a possibility of immediately verifying that which has been or may be discovered or assumed, demonstrate at every step that the work of the past has availed much, and that without it, it would be impossible to advance into the ocean of the unknown. They also show the possibility of becoming acquainted with fresh portions of this unknown, and compel us, while duly respecting the teachings of history, to cast aside classical illusions, and to engage in a work which not only gives mental satisfaction, but is also practically useful to all our fellow creatures. Thus, the desire to direct those thirsting for truth to the pure source of the science of the forces acting throughout nature forms the first and most important aim of this book. The time has arrived when a knowledge of physics and chemistry forms as important a part of education as that of the classics did 2 centuries ago. In those days, the nations which excelled in classical learning stood foremost, just as now the most advanced are those which are superior in the knowledge of the natural sciences, for they form the strength and characteristic of our times. In following the above and chief aim, I set myself a second object: to furnish a textbook for an elementary knowledge of chemistry, and so satisfy a want which undoubtedly exists among students and those who have recourse to chemistry either as a source of truth or welfare. Hence, although the fundamental object of this work was to express and embrace the general chemical teaching of the present day from a personal point of view, I have nevertheless striven throughout to maintain such a level as would render the principles of chemistry accessible to the beginner. Many aspects of this work are determined by this combination of requirements, which frequently differ widely. An issue was only possible under one condition, i.e., not to be carried away by what appears to be a plausible theory in explaining individual facts, and to always endeavor to transmit the simple truth of a given fact, extracting it from the vast store of the literature on the subject and from tried personal experience. In publishing a new edition of this work, I have striven to add any facts of importance recently discovered, and to revise the former edition in the above spirit. With this object, I have entirely gone over this edition, and a comparison of it with the former one will show that the additions and alterations have cost as much labor as many chapters of the work. I also wished to show, in an elementary treatise on chemistry, the striking advantages gained by the application of the periodic law, which I first saw in its entirety in the year 1869, when I was engaged in writing the first edition of this book, in which, indeed, the law was first enunciated. At that time, however, this law was not established so firmly as now, when so many of its consequences have been verified by the researches of numerous chemists, and especially by Roscoe, Lecoq de Boisbaudouin, Nielsen, Bronner, Thorpe, Carnelli, Laurie, Winkler, and others. The, to me, unexpectedly rapid success with which the teaching of the periodicity of the elements has spread in our science, and perhaps also the perseverance with which I collected in this work, and upon a new plan, the most important data respecting the elements and their mutual relations, explained sufficiently the fact that the former 5th 1889 edition of my work has been translated into English and German and is being translated into French. Deeply touched by the favorable opinions expressed by English men of science upon my book, I ascribe them chiefly to the periodic law placed at the basis of my treatise, and especially of the second part of the book, which contains a large amount of data having a special and sometimes quite unexpected bearing from the point of view of this law. As the entire scheme of this work is subordinated to the law of periodicity, which may be illustrated in a tabular form by placing the elements in series, groups, and periods, 2 such tables are given at the end of this preface. In this, the 6th edition, I have not altered any essential feature of the original work, and have retained those alterations which were introduced into the 5th edition. I have, however, added many newly discovered facts, and in this respect it is necessary to say a few words. Although all aspects of the simplest chemical relations are as far as possible equally developed in this book, yet, on looking back, I see that I have nevertheless given most attention to the so-called indefinite compounds, examples of which may be seen in solutions. I recur repeatedly to them, and to all the latest data respecting them, for in them I see a starting point for the future progress of our science, and to them I affiliate numerous instances of definite compounds, beginning with alloys and silicates, and ending with complex acids. There are 2 reasons for this. In the first place, this subject has deeply interested me from my youth. I have devoted a portion of my own researches to it, and therefore it occupied an important position even in the first edition of my book. Besides which, all that has been subsequently accomplished in our science, especially during the last 5 or 6 years, shows that at the present day an interest in these questions plays an important part in the minds of a large circle of contemporary workers in chemistry. This personal attachment, if I may so call it, to the question of solutions and such indefinite compounds must involuntarily have impressed itself upon my work. And in the later editions I have even had to strive not to give this subject a greater development than previously. So great was the material accumulated, which however does not yet give us the right to consider even the most elementary questions respecting solutions as solved. Thus, we cannot yet say what a solution really is. My own view is that a solution is a homogeneous liquid system of unstable dissociating compounds of the solvent with the substance dissolved. But although such a theory explains much to me, I cannot consider my opinion as proved, and therefore give it with some reserve as one of several hypotheses. As a subject yet far from solved, I might naturally have ignored it, or only mentioned it cursorily. But such a treatment of solution, although usual in elementary treatises on chemistry, would not have answered my views upon the subject of our science, and I wished that the reader might find in my book, beyond everything, an expression of all that a study of the subject built up for me. If in solutions I see and can frequently prove distinct evidences of the existence of those definite compounds which form the more generalized province of chemical data, I could not refrain from going into certain details respecting solutions. Otherwise, there would have remained no trace of that general idea, and in them we have only a certain instance of ordinary definite or atomic compounds subject to Dalton's laws. Having long had this idea, I wished to impress it upon the reader of my book, and it is this desire which forms the second of those chief reasons why I recur so frequently to solutions in this work. At present, my ideas respecting solutions are shared by few, but I trust that by degrees the instances I give will pave the way for their general recognition, and it is my hope that they may find adherents among those of my readers who are in a position to work out by experiment this difficult but highly interesting problem. In conclusion, I desire to record my thanks to V.D. Sapogennikov, who has corrected the proofs of the whole of this edition and compiled the indexes which greatly facilitate the search for those details which are scattered throughout the work. Dmitry Mendeleev. Footnote 1. Chemistry, like every other science, is at once a means and an end. It is a means of attaining certain practical results. Thus, by its assistance, the obtaining of matter in its various forms is facilitated. It shows new possibilities of availing ourselves of the forces of nature, indicates the methods of preparing many substances, points out their properties, etc. In this sense, chemistry is closely connected with the work of the manufacturer and the artisan. Its sphere is active, and is a means of promoting general welfare. Besides this honorable vocation, chemistry has another. With it, as with every other elaborated science, there are many lofty aspirations, the contemplation of which serves to inspire its workers and adherents. This contemplation comprises not only the principal data of the science, but also the generally accepted deductions, and also hypotheses which refer to phenomena as yet but imperfectly known. In this latter sense, scientific contemplation varies much with times and persons. It bears the stamp of creative power and embraces the highest forms of scientific progress. In that pure enjoyment experienced on approaching to the ideal, in that eagerness to draw aside the veil from the hidden truth, And even in that discord which exists between the various workers, we ought to see the surest pledges of further scientific progress. Science thus advances, discovering new truths, and at the same time obtaining practical results. The edifice of science not only requires material, but also a plan, and necessitates the work of preparing the materials, putting them together, working out the plans and the symmetrical proportions of the various parts, to conceive, understand, and grasp the whole symmetry of the scientific edifice, including its unfinished portions, is equivalent to tasting that enjoyment only conveyed by the highest forms of beauty and truth. Without the material, the plan alone is but a castle in the air, a mere possibility, whilst the material without a plan is but useless matter. All depends on the concordance of these materials with the plan and execution, and the general harmony thereby attained. In the work of science, the artisan, architect, and creator are very often one and the same individual, but sometimes, as in other walks of life, there is a difference between them. Sometimes the plan is preconceived. Sometimes it follows the preparation and accumulation of the raw material. Free access to the edifice of science is not only allowed to those who devised the plan, worked out the detailed drawings, prepared the materials, or piled up the brickwork, but also to all those who are desirous of making a close acquaintance with the plan and wish to avoid dwelling in the vaults or in the garrets where the useless lumber is stored. Knowing how contented, free, and joyful is life in the realm of science, one fervently wishes that many would enter its portals. On this account, many pages of this treatise are unwittingly stamped with the earnest desire that the habits of chemical contemplation, which I have endeavored to instill into the minds of my readers, will incite them to the further study of science. Science will then flourish in them, and by them on a fuller acquaintance not only with that little which is enclosed within the narrow limits of my work, but with the further learning which they must imbibe in order to make themselves masters of our science and partakers in its further advancement. Those who enlist in the cause of science have no reason to fear when they remember the urgent need for practical workers in the spheres of agriculture, arts, and manufacture. By summoning adherents to the work of theoretical chemistry, I am confident that I call them to a most useful labor, to the habit of dealing correctly with nature and its laws, and to the possibility of becoming truly practical men. In order to become actual chemists, it is necessary for beginners to be well and closely acquainted with three important branches of chemistry: analytical, organic, and theoretical. That part of chemistry which is dealt with in this treatise is only the groundwork of the edifice. For the learning and development of chemistry in its truest and fullest sense, beginners ought, in the first place, to turn their attention to the practical work of analytical chemistry. In the second place, to practical and theoretical acquaintance with some special chemical question, studying the original treatises of the investigators of the subject, at first under the direction of experienced teachers, because in working out particular facts, the faculty of judgment and of correct criticism becomes sharpened. In the third place, to a knowledge of current scientific questions through the special chemical journals and papers, and by intercourse with other chemists. The time has come to turn aside from visionary contemplation, from platonic aspirations, and from classical verbosity, and to enter the regions of actual labor for the common weal. to prove that the study of science is not only excellent education for youth, but that it instills the virtues of industry and veracity and creates solid national wealth, material and mental, which without it would be unobtainable. Science, which deals with the infinite, is itself without bounds. Footnote 2. I recommend those who are commencing the study of chemistry with my book to first read only what is printed in the large type, because in that part I have endeavored to concentrate all the fundamental, indispensable knowledge required for that study. In the footnotes, printed in small type, which should be read only after the large text has been mastered, certain details are discussed. They are either further examples or debatable questions on existing ideas which I thought useful to lay before those entering into the sphere of science, or certain historical and technical details which might be withdrawn from the fundamental portion of the book. Without intending to attain in my treatise to the completeness of a work of reference, I have still endeavored to express the principal developments of science as they concern the chemical elements viewed in that aspect in which they appear to me after long continued study of the subject and participation in the contemporary advance of knowledge. I have also placed my personal views, suppositions, and arguments in the footnotes, which are chiefly designed for details and references. But I have endeavored to avoid here, as in the text, not only all that I consider doubtful, but all those details which belong either to special branches of chemistry, for instance, to analytical, organic, physical, theoretical, physiological, agricultural, or technical chemistry, or to different branches of natural science which are more and more coming into closer and closer contact with chemistry. Chemistry, I am convinced, must occupy a place among the natural sciences side by side with mechanics, for mechanics treats of matter as a system of ponderable points having scarcely any individuality, and only standing in a certain state of mobile equilibrium. For chemistry, matter is an entire world of life, with an infinite variety of individuality both in the elements and in their combinations. In studying the general uniformity from a mechanical point of view, I think that the highest point of knowledge of nature cannot be attained without taking into account the individuality of things in which chemistry is set to seek for general higher laws. Mechanics may be likened to the science of statesmanship, chemistry to the sciences of jurisprudence and sociology. The general universe could not be built up without the particular individual universe, and would be a dry abstract were it not enlivened by the real variety of the individual world. Mechanics forms the classical basis of natural philosophy, while chemistry, as a comparatively new and still young science, already strives to, and will in the future, introduce a new, living aspect into the philosophy of nature. All the more, as chemistry alone is never at rest or anywhere dead. Its vital action has universal sway, and inevitably determines the general aspect of the universe. Just as the microscope and telescope enlarge the scope of vision and discover life in seeming immobility, so chemistry, in discovering and striving to discern the life of the invisible world of atoms and molecules and their ultimate limit of divisibility, will clearly introduce new and important problems into our conception of nature. And I think that its role, which is now considerable, will increase more and more in the future. That is, I think that in its future development it will occupy a place side by side with mechanics for the comprehension of the secrets of nature. But here we require some second Newton, and I have no doubt that he will soon appear. Principles of Chemistry. Introduction. The study of natural science, whose rapid development dates from the days of Galileo, died 1642, and Newton, died 1727, and its closer application to the external universe led to the separation of chemistry as a particular branch of natural philosophy, not only owing to the increasing store of observations and experiments relating to the mutual transformations of substances, but also and more especially because in addition to gravity, cohesion, heat, light, and electricity, it became necessary to recognize the existence of particular internal forces in the ultimate parts of all substances, forces which make themselves manifest in the transformations of substances into one another, but remain hidden or latent under ordinary circumstances, and whose existence cannot therefore be directly apprehended, and so for a long time remained unrecognized. The primary object of chemistry is the study of the homogeneous substances of which all the objects of the universe are made up, with the transformations of these substances into each other, and with the phenomena which accompany such transformations. Every chemical change or reaction, as it is called, can only take place under a condition of most intimate and close contact of the reacting substances, and is determined by the forces proper to the smallest invisible particles or molecules of matter. We must distinguish three chief classes of chemical transformations. 1. Combination is a reaction in which the union of two substances yields a new one, or in general terms, from a given number of substances, a lesser number is obtained. Thus, by heating a mixture of iron and sulfur, a single new substance is produced, iron sulfide, in which the constituent substances cannot be distinguished even by the highest magnifying power. Before the reaction, the iron could be separated from the mixture by a magnet, and the sulfur by dissolving it in certain oily liquids. In general, before combination, they might be mechanically separated from each other. But after combination, both substances penetrate into each other, and are then neither mechanically separable nor individually distinguishable. As a rule, reactions of direct combination are accompanied by an evolution of heat, and the common case of combustion, evolving heat, consists in the combination of combustible substances with a portion of the atmosphere, the gases and vapors contained in the smoke being the products of combination. 2. Reactions of decomposition are cases the reverse of those of combination, that is, in which one substance gives two, or in general, a given number of substances a greater number. Thus, by heating wood, and also coal and many animal or vegetable substances without access to air, a combustible gas, a watery liquid, tar, and carbon are obtained. It is in this way that tar, illuminating gas, and charcoal are prepared on a large scale. All limestones, for example, flagstones, chalk, or marble, are decomposed by heating to redness into lime and a peculiar gas called carbonic anhydride. A similar decomposition taking place, however, at a much lower temperature, proceeds with the green copper carbonate, which is contained in natural malachite. This example will be studied more in detail presently. Whilst heat is evolved in the ordinary reactions of combination, it is, on the contrary, absorbed in the reactions of decomposition. 3. The third class of chemical reactions, where the number of reacting substances is equal to the number of substances formed, may be considered as a simultaneous decomposition and combination. If, for instance, two compounds A and B are taken and they react on each other to form the substances C and D, then supposing that A is decomposed into D and E, and that E combines with B to form C, we have a reaction in which two substances A or DE and B were taken and two others, C or EB and D, were produced. Such reactions ought to be placed under the general term of reactions of rearrangement, and the particular case where two substances give two fresh ones, reactions of substitution. Thus, if a piece of iron be immersed in a solution of blue vitriol, copper sulfate, copper is formed, or rather separated out, and green vitriol, iron sulfate, which only differs from the blue vitriol in that the iron has replaced the copper, is obtained in solution. In this manner, iron may be coated with copper, so also copper with silver. Such reactions are frequently made use of in practice. The majority of the chemical changes which occur in nature and are made use of technically are very complicated, as they consist of an association of many separate and simultaneous combinations, decompositions, and replacements. It is chiefly due to this natural complexity of chemical phenomena that for so many centuries chemistry did not exist as an exact science. That is to say, that although many chemical changes were known and made use of, yet their real nature was unknown, nor could they be predicted or directed at will. Another reason for the tardy progress of chemical knowledge is the participation of gaseous substances, especially air, in many reactions. The true comprehension of air as a ponderable substance, and of gases in general as peculiar elastic and dispersive states of matter, was only arrived at in the 16th and 17th centuries, and it was only after this that the transformations of substances could form a science. Up to that time, without understanding the invisible and yet ponderable gaseous and vaporous states of substances, it was impossible to obtain any fundamental chemical evidence, because gases escaped from notice between the reacting and resultant substances. It is easy from the impression conveyed to us by the phenomena we observe to form the opinion that matter is created and destroyed. A whole mass of trees burn, and there only remains a little charcoal and ash, whilst from one small seed there grows little by little a majestic tree. In one case, matter seems to be destroyed, and in the other to be created. This conclusion is arrived at because the formation or consumption of gases, being under the circumstances invisible to the eye, is not observed. When wood burns, it undergoes a chemical change into gaseous products, which escape as smoke. A very simple experiment will prove this. By collecting the smoke, it may be observed that it contains gases which differ entirely from air, being incapable of supporting combustion or respiration. These gases may be weighed, and it will then be seen that their weight exceeds that of the wood taken. This increase in weight arises from the fact that in burning, the component parts of the wood combine with a portion of the air. In like manner, iron increases in weight by rusting. In burning gunpowder, its substance is not destroyed, but only converted into gases and smoke. So also in the growth of a tree, the seed does not increase in mass of itself and from itself, but grows because it absorbs gases from the atmosphere and sucks water and substances dissolved therein from the earth through its roots. The sap and solid substances which give plants their form are produced by these absorbed gases and liquids by complicated chemical processes. The gases and liquids are converted into solid substances by the plants themselves. Plants not only do not increase in size, but die in a gas which does not contain the constituents of air. When moist substances dry, they decrease in weight. When water evaporates, we know that it does not disappear, but will return from the atmosphere as rain, dew, and snow. When water is absorbed by the earth, it does not disappear there forever, but accumulates somewhere underground, from whence it afterwards flows forth as a spring. Thus, matter does not disappear and is not created, but only undergoes various physical and chemical transformations. That is to say, changes its locality and form. Matter remains on the earth in the same quantity as before. In a word, it is, so far as we are concerned, everlasting. It was difficult to submit this simple and primary truth of chemistry to investigation, but when once made clear, it rapidly spread, and now seems as natural and simple as many truths which have been acknowledged for ages. Marriott and other savants of the 17th century already suspected the existence of the law of the indestructibility of matter, but they made no efforts to express it or to apply it to the requirements of science. The experiments by means of which this simple law was arrived at were made during the latter half of the last century by the founder of modern chemistry, Lavoisier, the French academician and tax farmer. The numerous experiments of this savant were conducted with the aid of the balance, which is the only means of directly and accurately determining the quantity of matter. Lavoisier found, by weighing all the substances and even the apparatus used in every experiment, and then weighing the substances obtained after the chemical change, that the sum of the weights of the substances formed were always equal to the sum of the weights of the substances taken, or, in other words, matter is not created and does not disappear, or that matter is everlasting. This expression naturally includes a hypothesis, but our only aim in using it is to concisely express the following lengthy period: that in all experiments and in all the investigated phenomena of nature, it has never been observed that the weight of the substances formed was less or greater, as far as accuracy of weighing permits, than the weight of the substances originally taken, and as weight is proportional to mass or quantity of matter, it follows that no one has ever succeeded in observing a disappearance of matter or its appearance in fresh quantities. The law of the indestructibility of matter endows all chemical investigations with exactitude, as, on its basis, an equation may be formed for every chemical reaction. If in any reaction the weights of the substances taken be designated by the letters A, B, C, etc., and the weights of the substances formed by the letters M, N, O, etc., then A plus B plus C plus etc. equals M plus N plus O plus etc. Therefore, should the weight of one of the reacting or resultant substances be unknown, it may be determined by solving the equation. The chemist, in applying the law of the indestructibility of matter, and in making use of the chemical balance, must never lose sight of any one of the reacting or resultant substances. Should such an oversight be made, it will at once be remarked that the sum of the weights of the substances taken is unequal to the sum of the weights of the substances formed. All the progress made by chemistry during the end of the last and in the present century is entirely and immovably founded on the law of the indestructibility of matter. It is absolutely necessary in beginning the study of chemistry to become familiar with the simple truth which is expressed by this law, and for this purpose several examples elucidating its application will now be cited. 1. It is well known that iron rusts in damp air, and that when heated to redness in air it becomes coated with scoria, oxide, having, like rust, the appearance of an earthly substance resembling some of the iron ores from which metallic iron is extracted. If the iron is weighed before and after the formation of the scoria or rust, it will be found that the metal has increased in weight during the operation. It can easily be proved that this increase in weight is accomplished at the expense of the atmosphere, and mainly, as Lavoisier proved, at the expense of that portion which is called oxygen. In fact, in a vacuum, or in gases which do not contain oxygen, for instance in hydrogen or nitrogen, the iron neither rusts nor becomes coated with scoria. Had the iron not been weighed, the participation of the oxygen in the atmosphere in its transformation into an earthy substance might have easily passed unnoticed, as was formerly the case, when phenomena like the above were, for this reason, misunderstood. It is evident from the law of the indestructibility of matter that as the iron increases in weight in its conversion into rust, the latter must be a more complex substance than the iron itself, and its formation is due to a reaction of combination. We might form an entirely wrong opinion about it, and might, for instance, consider rust to be a simpler substance than iron, and explain the formation of rust as the removal of something from the iron. Such, indeed, was the general opinion prior to Lavoisier, when it was held that iron contained a certain unknown substance called phlogiston, and that rust was iron deprived of this supposed substance. 2. Copper carbonate in the form of a powder, or as the well-known green mineral called malachite, which is used for making ornaments, or as an ore for the extraction of copper, changes into a black substance called copper oxide when heated to redness. This black substance is also obtained by heating copper to redness in air. That is, it is the scoria or oxidation product of copper. The weight of the black oxide of copper left is less than that of the copper carbonate originally taken, and therefore we consider the reaction which occurred to have been one of decomposition, and that by it something was separated from the green copper carbonate, and in fact, by closing the orifice of the vessel in which the copper carbonate is heated with a well-fitting cork, through which a gas delivery tube passes, whose end is immersed under water, it will be observed that on heating, a gas is formed which bubbles through the water. This gas can be easily collected, as will presently be described, and it will be found to essentially differ from air in many respects. For instance, a burning taper is extinguished in it as if it had been plunged into water. If weighing had not proved to us that some substance had been separated, the formation of the gas might easily have escaped our notice, for it is colorless and transparent like air, and is therefore evolved without any striking feature. The carbonic anhydride evolved may be weighed, and it will be seen that the sum of the weights of the black copper oxide and carbonic anhydride is equal to the weight of the copper carbonate originally taken, and thus by carefully following out the various stages of all chemical reactions, we arrive at a confirmation of the law of the indestructibility of matter. 3. Red mercury oxide, which is formed as mercury rust by heating mercury and air, is decomposed like copper carbonate, only by heating more slowly and at a somewhat higher temperature, with the formation of the peculiar gas, oxygen. For this purpose, the mercury oxide is placed in a glass tube or retort, to which a gas delivery tube is attached by means of a cork. This tube is bent downwards, as shown in the drawing, Figure 1. The open end of the gas delivery tube is immersed in a vessel filled with water called a pneumatic trough. When the gas begins to be evolved in the retort, it is obliged, having no other outlet, to escape through the gas delivery tube into the water in the pneumatic trough, and therefore its evolution will be rendered visible by the bubbles coming from this tube. In heating the retort containing the mercury oxide, the air contained in the apparatus is first partly expelled, owing to its expansion by heat, and then the peculiar gas called oxygen is evolved, and may be easily collected as it comes off. For this purpose, a vessel, an ordinary cylinder, as in the drawing, is filled quite full with water and its mouth closed. It is then inverted and placed in this position under the water in the trough. The mouth is then opened. The cylinder will remain full of water. That is, the water will remain at a higher level in it than in the surrounding vessel, owing to the atmospheric pressure. The atmosphere presses on the surface of the water in the trough and prevents the water from flowing out of the cylinder. The mouth of the cylinder is placed over the end of the gas delivery tube, and the bubbles issuing from it will rise into the cylinder and displace the water contained in it. Gases are generally collected in this manner. When a sufficient quantity of gas has accumulated in the cylinder, it can be clearly shown that it is not air, but another gas which is distinguished by its capacity for vigorously supporting combustion. In order to show this, the cylinder is closed under water and removed from the bath. Its mouth is then turned upward, and a smoldering taper plunged into it. As is well known, a smoldering taper will be extinguished in air, but in the gas which is given off from red mercury oxide it burns clearly and vigorously, showing the property possessed by this gas for supporting combustion more energetically than air, and thus enabling it to be distinguished from the latter. It may be observed in this experiment that, besides the formation of oxygen, metallic mercury is formed, which, volatilizing at the high temperature required for the reaction, condenses on the cooler parts of the retort as a mirror or in globules. Thus, two substances, mercury and oxygen, are obtained by heating red mercury oxide. In this reaction, from one substance, two new substances are produced. That is, a decomposition has taken place. The means of collecting and investigating gases were known before Lavoisier's time, but he first showed the real part they played in the processes of many chemical changes which before his era were either wrongly understood, as will be afterwards explained, or were not explained at all, but only observed in their superficial aspects. This experiment on red mercury oxide has a special significance in the history of chemistry contemporary with Lavoisier, because the oxygen gas which is here evolved is contained in the atmosphere, and plays a most important part in nature, especially in the respiration of animals, in combustion in air, and in the formation of rusts or scoria, earths, as they were then called, from metals, that is, of earthy substances, like the ores from which metals are extracted. 4. in order to illustrate by experiment one more example of chemical change and the application of the law of the indestructibility of matter, we will consider the reaction between common table salt and lunar caustic, which is well known from its use in cauterizing wounds. By taking a clear solution of each and mixing them together, it will at once be observed that a solid white substance is formed, which settles to the bottom of the vessel and is insoluble in water. This substance may be separated from the solution by filtering. It is then found to be an entirely different substance from either of those taken originally in the solutions. This is at once evident from the fact that it does not dissolve in water. On evaporating the liquid which passed through the filter, it will be found to contain a new substance, unlike either table salt or lunar caustic, but like them, soluble in water. Thus table salt and lunar caustic, two substances soluble in water, produced by their mutual chemical reaction two new substances, one insoluble in water and the other remaining in solution. Here, from two substances, two others are obtained. Consequently, there occurred a reaction of substitution. The water served only to convert the reacting substances into a liquid and mobile state. If the lunar caustic and salt be dried and weighed, and if about 58½ grams of salt and 170 grams of lunar caustic be taken, then 143½ grams of insoluble silver chloride and 85 grams of sodium nitrate will be obtained. The sum of the weights of the reacting and resulting substances are seen to be similar and equal to 228½ grams, which necessarily follows from the law of the indestructibility of matter. Well, with another 60 pages left in the introduction, I think we'll stop there for this evening. I don't know about you, but I found that pretty interesting. Hopefully, you're no longer awake to hear this. But if you are, and you'd like something else to do besides consider just how cool chemistry is, won't you consider leaving us a positive review on iTunes? It really helps other people find our podcast. I'd like to thank everyone who's already done so. It's much appreciated. If you're interested in reading the principles of chemistry for yourself, you can find a link on our Goodreads account. Just go to goodreads.com/boringbooksforbedtime for a list of all the books read here to date. If you'd like to connect or suggest a boring book you'd like to hear read, catch us on Twitter @BoringBooksPod. We're always open for suggestions. You could also leave a comment on our Patreon account, where you'll find a number of exclusive perks for supporters. Thank you so much for joining me this evening. Until our next boring book,